we will continue the digital logic lecture 3, but before that we quickly go through the answers of the last day's lecture quiz. So, the last day's quiz there are 4 questions given and we see the answers. The first question was the convert the decimal number 0.252 decimal to binary with an error less than 1%. Now, as the error is 1%, so the what will be the error on 0.252? So, we will be multiplying this thing by 0.01 into the number 0.252. So, this is equal to 0.00252. Now, the truncation error, that means when we convert the decimal number to the binary, up to what digit we will convert it. So, if it is up to n bits, that means after decimal point if we take the value up to n bits, then we know the error is 2 to the power minus n. Last lecture we discussed that thing. So, this error should be less than this 1% error, means 0.00252. So, 2 to the power minus n is less than 0.00252, that can be written as 2 to the power n greater than 397. So, from this expression we can get the n if I take the log on both sides, then it will be log of 397 divided by log 2, and this is value equal to 8.63. Now, as n is the number of bits, so this should be some integer value, and that is why we are taking the nearest integer is 9, that is my nearest integer. So, when we convert 252 as binary, then we have to, if we take the number of bits after decimal point is not n, means n equal to 9, that means if you take 9 bits, then it will be, the error will be less than 1%. So, that means 0.252 in decimal is equal to 0.010000001 in binary, that means 9 bits after this decimal point. Now, we see the next question. Next one is the convert the following decimal numbers to hex and binary coded hex. The first one we see that 584 is the number. Now, 584, if I, this is in binary. So, if I want to convert this thing as some hexadecimal numbers, we know we have to divide that thing by the radix, and here the radix is 16. So, we divide 584 by 16, then it will be, quotient will be 36 and the remainder is 8. Again we divide, quotient is 2, remainder is 4. Again we divide, quotient is 0, remainder is 2. As the quotient is 0, so we stop division, and if I take in this order, then I am getting the 58410 is 248 in 16. So, this is my hexadecimal conversion. Now, another part is there, that binary coded hex. Now, if I want the binary coded hex, then what we have to do, then we will be taking, say again 584 in decimal. Now, we are converting it to binary. Now, we have to divide, here radix is 2, here radix is 2. So, we have to divide by 2. Now, if we get divide it by 2, we will be getting that it will be that as it is see my number becomes that it is simply it is 584 means this is 512 plus 64 plus 8. So, this will be my 584. So, how we can represent then? Then my 0th position means one value is 0, 2 is 0, 4 is 0, 1 8 is there. Then 16 is 0, 32 is 0, 64 is 1. Then 128 is 0, 256 is 0, then 512 bit is 1. So, this is my binary conversion. Just if I check, this is for checking, then this is my 0th position 1, 2, 3, 4, 5, 6, 7, 8, 9. That means 1 into 2 to the power 9 plus 1 into 2 to the power 6 plus 1 into 2 to the power 3. So, this is becomes 512 plus 64 plus 8, which is nothing but our 584 in decimal. So, I got my binary 584 10 is 1 0 0 1 0 0 1 0 0 0 in binary. Now, I want the binary coded hexadecimal. So, for hexadecimal, what last day we discussed that 4 bits we have to take together, and that should be from my LSB side. So, if I now mark this 4, then again this 4 and see 2 bits are left. So, I will put 2 zeros there, and now I take that this is my binary numbers. Now, if it is 0 0 1 0, this is 0 0 1 0 means this is my 2, then it is 0 1 0 0 means this is my 4, and 1 0 0 0 that is my 8. So, this is 248 in hex, which is matching to our previous result. That see, when I was converting from decimal to hexadecimal, it was converting to that. So, similarly, we can do the B part also. Now, we see the our third question. Convert the following binary number to octal and binary coded octal. So, this is totally similar. We will not continue this thing, because in the hexadecimal just now we have done there, we have taken 4 bit together. See that what we have done here, that we have taken, if it is already it is a binary number given 1 0 1 0 1, and this is 1 1 0 1. So, here if it is binary to octal, we have to do, that means 3 bits together, and here 2 bits are left. So, put 1 0 here, then it will be 3 bit. So, this part will become 0 1 0 means 2 and 1 0 1 means 5. So, this is my 2 5, and in this part again it will be only 1 1 4 bits are there. Again if I do, I will put 2 and then it will be 1 and again it is 5. So, it will be my 8. A simple that binary we will take 3 bits together and then we will put that thing the octal. Now, the next question was, the fourth question was, write the ASCII code for the message, the email is digital @iit.ac.in. So, ASCII means that for every character there is some 7-bit number. Now, see, it is very simple thing, and what we have done mainly for each character I have converted the 7-bit ASCII. As here the T is a capital one, so this is my the ASCII of capital T. So, this is my 1010100 is capital T, then this is H and this is, so this is my capital T, this is small h and this is small e. Now, see again the email. So, this E again this should be the same E, see that 1100101, here also this is 1100101. So, this is my E. Now, this is E M A. So, this is my I, this is my the ASCII code of small letter I, and this is L. See this again this is. So, here it should be I, and see the 1101001. So, this is my same ASCII code of I. Now, is digital, similarly I have written all the 7-bit code for each characters. Now, see this is at the rate. So, this is D I G I T A L. So, this should be my at the rate, this is my at the rate. See, this is 1 and 60, this 7-bit code or this 7-bit number is the actually the ASCII code of at the rate. Similarly, again this is I T and this is my dot. So, this is my dot. See again that A C. So, this should be again my dot. So, this is my D I G I T A L at the rate I I T dot A C dot in. In that way, I will be doing that thing. Okay. So, this should be my ASCII code of IIT.ac.in. Now, we start the today's lecture, that digital logic 3. See, first today first we see that one basic element of digital logic, and that is nothing but a switch. Already the introductory class we mentioned. Now, how one switch is implemented? Now, we know that a transistor can be used as a switch. Now, again we recapitulate from our knowledge, the previous knowledge, that it has the 3 things, that base, collector and emitter. So, this can be a switch. How this can be acted as a switch? That if the base is high, means that one 5-volt supply is applied at the base. Now, this makes the connection. So, if it makes the connection, that means the path is on, that means current will flow, or the base if the current flows, means the base becomes low, that means 0 volt. So, this will disconnect. So, simple that if base is high, that it will be disconnected. Now, this concept we can apply here. So, input and output. See, now the base is replaced by input and the emitter, the collector is replaced by the output, and this is the emitter is ground. So, now the if input is high, means the +5 voltage, and then the output will be low. Similarly, if the input is low, then obviously the switch, actually there is no connection, that means that output will be the high +5 volt. So, what we are getting, that see, if the input is a high means the plus 5 volt power supply, then we are getting output as a 0 volt, and input low it is 0 volt, output is a 5 volt. That means, this is the totally opposite thing we are getting. Now, this is the basic concept of that logic family. Now, exploiting this idea we will develop that our logic families. Now, we see that this is a NOT gate, the same thing we have taken, because NOT means what, that I want the what I am applying to the input, I want that this should be inverted. That means, if my input is A, say I am getting that my input is now some I am using some notation A. So, input high, this is a high voltage plus 5, and that I am representing as say 1. Then output is 0, say my output notation is O. So, if it is 1 means 5 volt, I am getting output as 0. So, this is my input, this is my output. Now, reverse one, if A is 0, then output becomes 1, that means output is opposite. We are telling this as the NOT gate. Now, we see, now this is the when we represent this switching concept, we are telling this is my NOT gate symbol. That means, my input A and that output is the complement of this thing, or it is inverted. That means, when it is 0, this becomes 1, when it is 1, this becomes 0, and this symbol we used for the NOT gate. We call this is my NOT gate. Now, another thing is the truth table. So, truth table describes inputs and outputs in terms of ones and zeros rather than voltage levels. So, just now what we have seen, see the input I have given a 5 volt power supply. So, this is my voltage level, either my voltage level is plus 5 volt or 0 volt. Now, if I represent this plus 5 volt as a 1 and the 0 volt as the 0, then the function, the way we are representing this function, that we are calling as the truth table. See, so this describes input output terms in ones and zeros rather than voltage levels. So, just now what we have seen, that input A, that becomes, as it is only single input line. So, either it can be 0 or it can be 1, and output will be, if it is 0 it will be 1, if it is 1 it will be 0. So, this is the truth table concept. Now we see that it is slightly complex things. See, if the output is 1 here, when output will be 1? If both the switch are connected, that means, see here this switch will also be connected, here this switch also be connected, this is also connected, this should be also be connected. So, what I want for that? I want then this input 1 that should be equal to the plus 5 volt, I want my input 2 should also be plus 5 volt. Then this should be my output should be 1. So, output is input 1 and AND2 input 2. That means, there should, if it for this is it, there will be 2 inputs and 1 output. So, how I represent that thing? See, I can represent by this circuit by this notation. So, this is normally called the AND gate, means the if it is 2 input, that means if both the inputs are 1, see then both the switches are connected and that means output is 1. Now, if any one of the switch is disconnected, then actually output my is 0. So, any one of the switches disconnected means my input is 0 or 0 volt if I consider voltage level. That means, my if I put or we write in this way that say my input, this one is either this one is disconnected, this is disconnected means that input is 0 and this is connected means output is 1, but whatever be the case, then output is 0. Even if it is 1 and if it is 0, then also it is 0, output is 0. And if both are disconnected, then obviously the output is 0, because there is no path for current flow. So, now if we represent this thing by in truth table fashion, means we describe the input output relation by using the notation of zeros and ones, where the same thing that 1 means that some high voltage, 0 means some low voltage, but instead of voltage levels I am using the 0 and 1, and that we have defined as the truth table. So, if we see that, see the truth table of AND gate. So, this is if it is a 2 input AND gate and 2 input 1 output. So, just now what we have drawn, that this was the, this is another logic gate, we call this is my 2 input and 1 output. Say this is input is A, another input is B and this is my output say Z, or say I am taking this is as O. Okay. So, this is my output O. Now, what we can see that if AB, the first value is that A and both the inputs are 0 0. That means, if A equal to 0 and B equal to 0, now what will be the value? That means both the switches are disconnected. So, the output will be 0. So, this is the first value. Now, if A is 0, but B is 1, that means remember that one switch is disconnected and in this case the again the output will be 0. Similar thing happens for the third case, and only the output will be 1 when both the inputs are 1, means both the switch are connected. So, when the input is only 1 1, then only I am getting a 1 at the output. So, here only if both the inputs are high, that means plus 5 volt, then only I am getting a plus 5 or 1 at the output. So, this is the truth table of AND gate. Now, we see the another basic gate and called the OR gate. So, see here the switches are connected in a slightly different way. See that in previous cases it was connected, we can tell these are in series connection, the two switches as if they are connected in this way. Now, here they are connected in parallel. Now, see that say that this line is a some plus 5 volt power supply is attached, that is to the it is connected here. Now, at the base we are applying the some input and here also some different input B. Now, if I change my voltage at these two lines, what will happen? How it will behave? So, the output is 1 means now 1 means this is a plus 5 voltage, output is 1 if A is 1 or if B is 1, means if either one of these switch is connected, then actually it is getting a path. So, it will be flowing and so the output is 1, that means this 5 volt I am getting here, and if both are connected then obviously it will be 1, but if both are disconnected only that is the situation when the output will be 0, because if both are disconnected then there does not exist any path, there does not exist any path to get this high voltage in this line. So, if we summarize what will happen, output is 1 if A is 1 or if B is 1 and output is written as A or B. So, this is my concept of OR gate. How the gate is denoted? So, the gate is denoted like this notation. So, the two inputs are A and B, these are the two inputs and only one output, again this is a 2 input 1 output OR gate, and normally the notation is A plus B, and the AND gate normally it is written as A dot B. So, for AND gate this is written as A and B is A dot B, this is the notation, and for the OR gate this is A plus B. Okay. Then what will be the truth table? See the similar way, this is a 2 input A B and output O. So, again if we draw, so if we draw the OR gate, this is a 2 input OR. Now, input lines I have given A and B and output is O. So, if A B is 0 0, then both are disconnected, both the switch. So, output will be 0. If A is 0, B is 1 or A is 1, B is 0. So, if any one of the switch is connected, that means it is getting a path. So, output becomes 1. If both are connected, then obviously it is getting in both the direction, it is getting the path. So, this becomes 1. So, this is my truth table of the OR gate. Now, if I put a AND gate, so mainly these three are the, so far we get 3 basic gates. That NOT, then NOT gate, then AND gate, and then OR gate. Now, from these 3 basic gates, again I can generate 2 other very important gates. Again they will be treated as basic. So, that means, if say this is 1 2 input AND gate, and if I put a NOT gate here, then I am telling these I am converting as a as the 2 input NAND, that means and this notation, that means this notation always means that it is inverted, that this is my A dot B complement. So, this is my NAND gate, and it is normally this is represented as NAND. Similarly, if I take instead of the AND, if I take a 2 input OR, then what will happen? I take a 2 input OR and I put a NOT gate here. So, this is my A, B. So, this is A plus B, and this will be A plus B complement. And these whole things again similar way, if I replace this 2, it will be a NOR, just OR and with a circle at the end, this will be A, B, and it will be A plus B complement. So, this is my NOR. Again this NAND and NOR are 2 other basic gates. Now, what will be the truth table of this NAND and NOR? See what we have seen, that if it is a 2 input NAND, then it is actually equal to what we can write, the 2 input and that is complemented. So, what will be the truth table? If I write together, say this is my inputs, the A and B, these are my outputs, say this is the, I am giving O output for AND, and this is the output O for NAND. Then see what will be the thing. Say A B, it can take 2 values, because 2 binary inputs means 2 square 4. So, if it is 0 0, that what will be the AND? Remember, it will be obviously it will be 0, no path, and it is the complement. So, O NAND is already we have written that 2 input NAND is a 2 input and complement. So, 0 complement means this becomes 1. Similarly, if it is a 0 and 1, again it will be 0 So, this will be 1, it will be 1 0, then also it is 0, then complement of this is 1. If it is 1 1, then only I am getting a 1 output at the AND gate, and obviously this will be 0. So, see the output or the truth table output of NAND is the complement of the truth table output for the AND. So, similarly, I can get the NOR, because my 2 input NOR is nothing but the 2 input or complemented. So, similar way, if I can draw the truth table, then my inputs are similarly A and B, outputs are output for OR and output for NOR. Again you take that two values. If it is 0 0, output for OR is 0. If it is, now it is complemented or inverted, so it will be 1. Now, if any one of the input is 1, then actually the output will be 1, it will be 0. If it is 1 0, then it will be 1, it will be 0. If it is 1 1, then OR is 1 and output is 0. So, this is my truth table of the OR gate. Now, we see that what do we mean by some abstraction. Now, in computer science, the term abstraction refers to the practice of defining and using objects or systems based on the high level functions they provide. So, just now what we have seen, the AND gate, the OR gate, these are nothing but some functions. Now, a big system I can represent by with using this a number of these AND and OR gates. Now, abstraction is that how we are defining a object or a big system high level on the high level functions, and this is the abstraction in computer science. So, if the implementation changes, our high level work is not affected. That means, if your that AND gate OR gate, that means say I am taking one example. Say I am taking one high level system. Say one high level system, I am just giving a black box, and it is represented, say this is represented as, say one sub system is represented like some 2 input AND, a number of 2 input ANDs, then some OR, then say some NAND or NOR gate I am giving NOR. So, it is some, so it has another input, it has also another input in this way. Now, so this is one circuit. Now, if I change, because that is it will give some say it has 1, 2, 3, 4, 5, 6 inputs and one output. Okay. Now, if I change this some of the AND or OR gates, So, still I am getting the same functions. That means, the truth table it is giving that for 6 inputs there will be some some value 0 1 0 1. Here also I am getting some output. These are for my inputs and these are my outputs. Now, if I change some of this thing, still the behavior is same. That means, for the same input I am getting the same output. Say if it is my input is say 0 1 0 1 0 1, say I am getting 1 as the output. Now, even if I change some of the gates, still I am getting a 1. Okay. Then abstraction means that how it is implemented, whether this AND gate is OR gate or the previous AND OR gate is replaced by an OR gate, it does not affect. Okay. So, this is we are calling that abstraction of a digital circuits. Now, we give the abstraction as an example. Just now I have taken that one big system I have represented by some logic gates, AND, OR, NOT, NAND, NOR. These are the some basic gates we just now read, and using that I have given. Now, these logic gates, we can work with the logic gates knowing only their function. Means that just now we have seen that if it is a 2 input AND gate, that it will be output will be only 1 when the 2 inputs are 1. So, these are we are calling the function of the AND gate, that means output is 1 only if inputs are either 0 or 1. It is not needed to know how gate is constructed from transistors. So, similarly, that I am getting the behavior of a large system, I do not know that, or it is not needed, to know that how the gates are connected or which gates are connected. Okay. So, similarly, another example is the Boolean algebra. So, we can work with the Boolean expressions only the properties or laws. It is not needed to know the details of what the variables represent. So, already we have read the logic gates, and now later we will be seeing that Boolean algebra again that can be, or Boolean expressions and some of the operations defined on the Boolean expressions or Boolean variables, that we can tell the Boolean algebra, that also can be used for the abstraction for digital systems. Now, so far we have read the logic circuit and truth table. So, now again we will read the how these can be used as a Boolean expression. Now, just we see that some expressions using some Boolean variables. And what are Boolean variables? Boolean variables means it can take one variable can take only 2 values, either 0 or 1, that means our binary variable. So, these are Boolean, and using that some expression is written. So, this is Boolean expression. Now, how they are related? So, this that from if a Boolean expression is given, this arrow means if one expression is given, from there I can draw a logic circuit. Logic circuit means one circuit consists of a number of logic gates, and the gates are of type just now we have read the OR, AND, NOT, NAND, NOT, etc. Now, if the Boolean expression is given, I can draw a truth table. What is truth table? Truth table is the description of inputs and outputs with respect to zeros and ones only to describe its overall behavior. Now, see, from the logic circuit to Boolean expression, if a Boolean expression is given, I can draw the logic circuit. In reverse direction, if the logic circuit is given, from there I can also compute the Boolean expression. So, if the logic circuit is given, I can draw the truth table, and if the truth table is given, the logic circuit can easily be drawn from the truth table. If the truth table is given, from the you can compute the Boolean, you can write the Boolean expression for the circuits. So, this is called that the triangle or the abstraction triangle. Now, one by one we will see first that how, if the logic circuit is given, how we can write the Boolean expression, how we can write the truth table. Then we will be seeing that if the expression is given, how we can draw the logic circuit, how we can the truth table. If the truth table is given, how the Boolean expression can be written, how the logic circuit can be written. First we see Boolean expression to logic circuit. Now, to draw a circuit from a Boolean expression. So, from the left, make an input line for each variable. Say I have some variable. Okay, first we see, then we will be giving example. First we read the rules of variation. From the left, make an input line for each variable. Next, put a NOT gate in for each variable that appears negated in the expression. Still working from left to right, build up circuits for the sub expressions from simple to complex. See, first we take one example. Say one, I am taking A and B are two Boolean variables. Okay. Boolean variables. So, that means A and B can take values 0 or 1. Now, say one expression is given, say A, simple expression I am taking A plus B. That means, these are the two Boolean variables. This is one operator. What operator it is? Our OR operator. So, we know that for this one logic gate exists. For one plus, I know that my logic gate is OR. Okay. So, from left, what was the rule? The left, just we give a notation for variable, or say this is or one line. So, A will be replaced by a line. Similarly, B will be replaced by a line. Then it will be replaced by my logic operator, by my logic gate. So, this is nothing but your Z equal to, this is the circuit. So, if the expression Z equal to A plus B, then this is my logic circuit for that. Now, say Z equal to say A dot B complement is given. Then for A, one line. Now, for B, another line, and as it is complemented or inverted, so I will put a NOT gate there. So, this is my actually B complemented. Then it is a dot, means it will be replaced by a AND gate, and this is my Z. So, this will be the Z equal to A B bar. So, simple OR gate and the AND gate can be extracted if these two Boolean expressions are given. Now, we see a slightly bigger example. See, one logic circuit is given, that is or a expression is given, that A B complement plus A plus B complement dot B. Actually here we can tell that AND is there, this is dot, this is also dot. Okay. Now, for see there are two variables only, A and B. So, I give two lines A and B. Now, see I have another, this will be B complement. So, I have another variable needed, that is complement of B. So, this is B complemented line. Okay, this is for that one NOT gate is put on the path of B. Now, I want A B bar, means A dot B bar. So, I have A line, I have B bar line. So, I will put one 2 input, one output AND gate, that whose output is that A B bar. So, these sub expressions for A B bar, that is this is the circuit for the sub expressions A B bar. Now, still I have another sub expression. Now, that is A plus B bar dot B. So, first we see how I can draw A plus B bar. Now, see A is available, B is also available. So, A and B I give a OR, plus means my OR operation. So, one 2 input OR gate and the output will be A plus B. So, this is the simple sub expression of A plus B, the extra that is added with the previous picture. Now, A plus B complement. So, simple, I will put one NOT gate at the as A plus B as the input, or other way I can tell A plus B is directly applied as the input of a NOT gate or a inverter, and then output will be A plus B complement. Now, again in the expression I need another, it should be A plus B complement to B, A plus B complement B. So, now see this is my A plus B complement and this B is available. So, actually this B is going here and this is my B and this is a 2 input AND gate. So, A plus B complement B. So, output of this AND gate is A plus B complement B. Now, the full expression we see, this is my A B bar, the first part A B bar, and the right hand the next portion is A plus B complement B, that is the another input, these two input are fed to one OR, because it is a plus, plus means my OR, 2 input OR gate. So, this is my output Z. So, I get my output Z as the A B bar plus A plus B complement B. So, in this way we can, what we have done, if a Boolean expression is given, then we can draw a logic circuit, that means a number of logic gates with the interconnections so that it realizes that expressions, means that if I give the input values or in terms of zeros and ones, what will be the output of that expression. That means that Boolean what value will be evaluated, or the output value of the expression evaluated, the logic circuit should evaluate the same value for the same input set, and then we can tell that the Boolean expression is correctly converted to the logic circuit. So, only we have seen the this portions, the our in the triangle, the Boolean expression to the logic circuits part. Okay. So, next day we will be seeing the other conversions of the circuit. Today we will end here. Today we will start discussion on Boolean algebra. So, last day we have discussed that the design of digital circuits, and just to design the digital circuits, what are the basic needs that we have discussed in the introductory class. So, if we recapitulate quickly the summary of the last day's lecture, that we found that three things, that logic circuits, truth table or Boolean expressions, that any one of these things is necessary. Now, last day we have seen some Boolean expressions, that means given a digital design to be built up, first we have identified as some of the expressions, or the if the truth tables, we have seen that how the truth table can be built up from the Boolean expressions, and again from the Boolean expression the logic circuits can also be built up. Now, from logic circuit, if the logic circuit is given, from there the Boolean expression can also be evaluated. Similarly, if the logic circuit is given, the truth table can be constructed. If the truth table is given, then the logic circuit can be designed from the truth table. So, today we will see that how this Boolean expression can be built up.